Okay, so chapter 4, this is going to be atoms and elements. If you're wondering, this chemistry sure as hell isn't a lot of chemicals. This was why. For your information, does anybody know when you should have actually learned conversion factors? When the state required, nationally required to learn conversion factors? Middle school. It's on the middle school examinations. Oh, yeah. It's on their teaching charter. Yeah. Unfortunately, don't feel bad if you didn't. Like, it's a pretty common thing, unfortunately, in the U.S. And in fact, we were back in the 1980s, and for like 50 years, we were required to by treaty teach it in middle school.
To be fair, COVID was our.
Yes, yeah, and I mean, even without COVID, it was already a thing that was a problem. Like, so don't feel bad. It's okay. That's why we did all that review, right? And then we had a whole lab period that we did it. Okay, so now we're going to talk about atoms and elements. So elements, these are going to be pure substances that which all other things are built. They cannot be broken down into similar substances and still have the same properties at all. Okay? Once you get below atoms, you don't have copper, you don't have sulfur, you don't have any of those things, okay? Once you get it down past atoms. They're listed on the inside front cover of the text. They are the periodic table. Everybody seen the periodic table? Fantastic. You know what I really, this was a before my time thing, but they used to do full periodic tables that you could fold out from books. Okay? When we get on the periodic table, I'll show you why that's important. But they stopped doing that way before my time, and it's really a shame. Yeah, it'd actually be very helpful. So the element names, these come from all sorts of things. Planets, mythological figures, minerals, colors, geographic locations, famous people. Basically, there's a committee that's done the naming. Funny enough, committees of scientists are like kids. I'm not joking. You get enough smart people in a room, and it starts sounding like a bunch of 3-year-olds arguing. And so there was like a it was over a 12-year period where none of the new atoms and elements were getting assigned names because they got into a big fight, and then basically people had to age out. So whatever. This is, of course, uranium, planet Uranus. Here we have titanium. That's actually a Titan from mythology. Anyways, chlorine is chlorus. It's actually the gas is a greenish yellow, and so it's given that name. It's the Greek for greenish yellow gas. Iodase, violet. If you look at a liquid of iodine, it's a really deep violet shade. Okay. Anyways, here's TS, stands for Tennessee, and that's the name of the element right there. Okay. There's actually a very, very good lab here. Does anybody know what the lab is? Oak Ridge boys. Oak Ridge lab. Okay. Anyways. So the chemical symbols, these are 1 or 2 letter abbreviations for an element's name. Can you have a 3-letter symbol? Nope, no 3-letter symbols. When chemical symbols contain 2 letters, the second letter is not capitalized, only the first is ever capitalized. CO is the chemical symbol for cobalt, for example. If you were to say C capital O, that would not be cobalt, would it? That would be carbon monoxide, okay? And having cobalt and having carbon monoxide in the room with you is a very different thing. Yeah. We have a fair amount of cobalt in the room with us right now, very likely in the various different steels around you. It helps it make it more resistant to corrosion. Hopefully we don't have a lot of carbon monoxide in the room with us, because that is poisonous. Poisonous gas. Okay. Now, these are the 1-letter and 2-letter symbols of various different elements here. Does anybody have any questions about that so far? Okay. Now note that some of them are very nicely done, like carbon is C, cobalt is CO. Those make a lot of sense, right? Yeah. Some of them are not so nicely done. Okay, these are nice examples. Unfortunately, other things, they just, for whatever reasons, were not able to, or there's historical context there. Okay? Like iron, for example, is a big one. Fe for the symbol. Okay? This right here is some of the more common elements and their symbols. Gold is another example where it got a little weird. And that's because of historical relevance of the naming. Gold is actually named after aurum, which is gold in Latin, essentially. Yeah. I know, right? So, most chemical symbols, again, are going to be using letters from their current name of the elements. However, some of them have names from historical relevance, okay? Particularly Greek and Latin, right? So, for example, gold, we call it gold in English. However, keep in mind that when the periodic table is being developed, English-speaking scientists were actually kind of a minority, okay? They weren't a particularly large group that would be anybody cared about. Wasn't a lot of good English scientists at the time. And so, for example, the one language everybody could kind of agree that would be useful would be Latin and Greek, okay? And that's why we have, for example, the symbol for gold is Au, that's from aurum. The symbol of silver, Ag, argentum. Okay? Let's go ahead and try a question here. This is where we start having the plickers actually being super incorporated into it. Ooh, ah. So beautiful. Okay, so the chemical symbol for iodine: iron, magnesium, zinc, and lithium. Pick which one you think has it correct. Okay. Anybody that's not ready to answer, please flip your card upside down. Okay. Did I get you? Yep. Okay. Okay. All right, and yeah, there you go. Yeah, that was some of those, right? So keep in mind that some of these do not have the first letter. Again, that's a historical thing for some of these. For some of these, they have like ZN instead of Z. Partially because like Z is actually the symbol that means something, okay? And they wanted to avoid that. It literally means the number of protons, okay? L, they already had L for several things, so they didn't want to use L alone, right? Yeah. Iron is just a kind of weird one, unfortunately. It's another one of those where they took, it's actually a fire god, if I remember. No, not fire god. That's copper. It's a like spirit of the iron thing. Yeah, it's a weird mythological one. Okay. Okay, let's try the next one. Whoops. Give the names of the elements with the symbols P, A, R, M, N, B, E, K. Okay. Fantastic. Cool. Yeah, it turned out good. Okay, and so right here again, It's this one right here. So this one, the answers right here are a little bit more challenging, aren't they? Did anybody notice I put some of these where they're not even elements? Yeah. Yeah. So this is phosphorus, argon, magnesium, beryllium, potassium. Okay. Okay. All right. Okay, so why is it important to know something about the elements? Well, for example, we have here mercury. Its symbol is Hg. It's a silvery, shiny element. It's a liquid at room temperature. It's one of the very few metals that are liquid at room temperature, and the few things on the periodic table that are liquid at room temperature, which is quite unusual, actually. Mercury can enter the body through several different pathways. We have inhaled mercury vapor, contact with the skin, ingestion of foods and water that have been contaminated with mercury. Anybody ever seen Alice in Wonderland? Okay. You ever seen the Mad Hatter? What poisoning does he have again? Mercury? How do you get that poisoning? Yeah, that's how you make the felt on the stiff hats back in the Victorian age. What symptoms does he have from mercury poisoning? Not just crazy. He has nerve damage. Yeah. So he does have impulse control, but he wouldn't actually be just crazy from the mercury poisoning. However, in his case, he is very clumsy. He has difficulty grasping things. He has impulse control issues. And so he tends to burst out in random fits of rage sort of stuff. And he's very frustrated that he can't use his hands properly and can't do his hat making. And so his entire career and what he's famous for can't be done. Yeah. And it's literally a political commentary on that, right? And so in the body, the mercury actually destroys proteins. It disrupts cell functions. Long-term exposure to the mercury, like the Mad Hatter, will cause damage to the brain and kidneys. This can cause mental retardation over a long time period of time. That's why women don't eat fish oftentimes when they're pregnant. It's because fish can be very high in mercury, and this would then cause damage to the fetus's brain, and that would be long term. This can decrease physical development as well. Scientists can use blood, urine, and hair samples to test for mercury. Anybody know why dams became sort of a passé thing? Like hydropower is a lot less talked about now as like a solution to the energy problems. Why isn't it talked as much anymore? Mercury contamination. So for a dam to work, you have to flood an area behind the dam to build up pressure behind it. And so that flooding that area behind the dam oftentimes brings mercury up into the water. And it'll actually start poisoning the water sources. Yeah. Now it is a somewhat short-lived thing. It'll sort of dissipate after the course of about 50 to 60 years. Unfortunately, in 50 to 60 years, most of your population has been poisoned with mercury. So, yeah. Anyways, that's why dams have not been, and hydropower has not been talked about as much anymore, in case you're curious. This right here is the periodic table. And so again, the periodic table is going to organize the 118 elements at the time of this publication into groups with similar properties and places them in order of increasing atomic mass. That's not actually correct in the modern periodic table. It's actually increasing atomic number, meaning the number of protons, which we'll talk a bit more about in a bit. Do you guys know what protons, electrons, and neutrons are? Okay. Yeah, it should have been a middle school chemistry thing, middle school science, but no? Was it? Oh, wow. Okay. Oh, wow. Anyways, so yes, it's actually the number of protons here, and that would be the, that would be how we organize the periodic table. Notice these are the different groups that they can be placed in. This is the alkali metals, this is the alkaline earth metals. This right here is a transition elements. This doesn't have any real common names to them. Sometimes they're referred to as the one in this period right here. So like silicates, silicon-like, oxides, oxygen-like, that sort of thing. These right here would be the halogens. These would then be the noble gases. So in 1869, Dmitry Mendeleev is probably the most famous character to have come up with the periodic table, and he's the one that typically is credited with it. There was actually 4 independent people that came up with it around the same time within a decade or two. There's actually a couple people that came up with it before him, but he's the most interesting. If you ever want to see a cool biography, Dmitry Mendeleev is an interesting character. Okay? So again, he created a periodic table, arranged the elements by increasing mass, arranged elements into groups with similar properties, and actually I predicted several elements. And so this right here is actually the modern periodic table right there. Everybody see that okay? Okay. And you will notice again that is arranged not by mass, but it's arranged by atomic number, which is this number on the top that says 1, 2, 3, 4, 5, 6, 7, 8, etc. Okay? Now, what does this mean here?
That's where those fit in.
Yeah. You actually split the periodic table in half here. It's actually here. And move this part to the right. And so the periodic table does not fit well on a book page. It actually would fit better on like a newspaper sort of fold out. And in the old day, they used to actually have fold out periodic tables in your books. And so you'd fold it out and you could see the periodic table as it's meant to be. You'll have to look online now because it basically, you basically can't get a periodic table that is folded out without going online now. So on your periodic table, elements are going to be arranged according to the groups that have similar properties. These vertical columns right here, which is, for example, group 1A, group 2A, 3A, 4A, 5A. You get the idea, right? Okay. And again, they have similar properties. So the periods are going to be the horizontal rows. Everybody remembers horizontal, right? These are the periods right here, going across. Okay, and they're going to be counted from top to bottom. They're periods 1 through 7 right now, though theoretically we might find something below those. Okay, they're probably very, very radioactive though, and it'd be very short-lived. Okay. Period 1 is going to contain only 2 elements. This is hydrogen and helium up here. Period 2 contains the next period right here, which goes across. Okay. Now, can anybody tell me after we're done with this period how much of the mass of the solar system we've already accounted for? 90-something%. Okay? This period here already accounts for almost 70%. And the next period accounts for the vast majority of that. Everything as we go lower in the periods gets much, much rarer in the solar system. Okay? Okay, and then period 3 is these right here. Anybody have any questions so far? Fantastic. So the group numbers are going to, again, identify the vertical columns of the periodic table. They're written in 2 ways. Please remember, you can ask me questions through email. You can ask me questions in person. You can come to office hours. If, for whatever reason, you're scared of my office hours and asking me questions, feel free to talk to tutor, okay? Okay. But get help if you need help. So, again, we're going to identify the vertical columns in the periodic table. These will have group numbers. The letter A is representative of the elements 1A through 8A. The letter B is the transition elements on most periodic tables. Sometimes they don't bother with that, and they just go 1 to 18. Okay? Yeah. The numbers 1 through 18 are going to be used from the columns from left to right, and that's just the numbering off of the columns. Okay. And again, this is what that looks like. Everybody see it okay? Fantastic. You will notice that the bottom is oftentimes dropped, the lanthanides and actinides, from the periodic table, because they do very little chemistry in the world around us, mostly because they're incredibly rare and they're radioactive as well. Yeah. So you wouldn't want them in the products that you're holding, though there's really cool radioactive batteries now. Yeah. They can give power for 100 years. Yeah. I know. Awesome, right? Okay, so you're all looking like me, like, no. No radioactive batteries, Dr. Clausen. So representative elements are, again, going to be these right here. And we have group 1. This is called the alkali metals. Everybody ever seen an alkali battery? At the grocery store? In your remote control at your home? Okay. And so those have typically a sodium, potassium in them, and they get their names from these alkali metals. Okay? Ultimately from these alkali metals. We also have the alkaline earth metals right here, and that's these right here. And you can see calcium in there and magnesium, oftentimes talked about in terms of health, right? Right here we have groups 3A, 4A, 5A, 6A, not really referred to as any super specific naming, okay? Halogens are the next group that has a specific name, that's 7A, and these are named after the halides or halogens, and again that is the chlorine, that is bromine, that is fluorine, etc. Okay? And then the noble gases, these are these ones at the very end right there, and they're helium, neon, argon, krypton, xenon, etc. These ones down in here are usually ignored because they're more metallic, and they tend to not be so gaseous. But, yeah, these ones right here, anybody know why they're called noble? Yeah, they're snooty, right? They don't react with other stuff. Okay, so these are the alkali metals. If you throw these in water, anybody know what happens? Yeah, they go boom. The ones on the top of the periodic table actually usually don't go boom right away. They actually just skip around on the surface of the water and let off a little bit of steam and flame. Potassium and below, they'll go boom usually. Lithium, if purified enough and put into a nice mesh, like in a battery, can go boom. Anybody ever seen a Tesla go on a cold day? No? Look it up on YouTube. They like blow up and take out the charging stations. Yeah. The batteries can be quite explosive, and it has to do with having rapid temperature shifts. So when it gets very cold and very hot, your cell phones, your Teslas, all those, it's best not to charge them when they're really hot and cold. Okay? They have a tendency to become much more flammable when you do that. By the way, you do know your phone is actually an explosive, right? Yeah. You ever seen the pictures on the outside of the shipping boxes for these? Shows a person with a knife trying to stab into the box and then flames coming out at them. And it says flammable on the side. That's because the lithium batteries. All right. So these are halogens, by the way. This is chlorine, bromine, and iodine. Ooh, they're so pretty, aren't they? Okay. And that's the halogens right there. Very reactive. They would not stay as those gases if you were to open the gas. Okay, they'd react with whatever you had around them usually because they are quite reactive. Okay, so let's look at the plickers. Which option is in group 7A? So which is group 7A? Is it O, F, oxygen, Na? I think you're kitty corner. There you go. Okay. I think your hand's covering it. Yeah, we found them right. Got it? Okay. Okay. And thank you for letting me know. That is the fluorine. O stands for oxygen, which doesn't have a specific naming on it, but is 6A. Sodium is down here. That's actually the first group. Okay. All right, so let's talk about metals, nonmetals, and metalloids. So you may have noticed a heavy like zigzag that was on the periodic tables, and it's this like bolded zigzag that runs down the side there. Okay, that's actually the division point between metals and nonmetals. Everything that has two sides on that is usually considered what's called a metalloid. Okay? Mm-hmm.
So is acetide considered a halogen or is it a metalloid?
This one right here?
No, that's oxide.
Okay, this one? Okay. It's both. So halogen doesn't necessarily mean it's a metal, non-metal, whatever. Okay? It just means it's in this group right there. So, for example, the fluorine, chlorine, iodine, all of those are nonmetals. Okay? And then when we get down here, the ATTS, those are now metalloids. Okay?
And
And
most periodic tables don't have those as metalloids. They have them as halogens. Most like the periodic tables
Yeah.
have it as that is not a metalloid that gets.
So, full disclosure, these metalloids, boron, aluminum, this right here knows the two sides isn't listed in this one. These pop in and out of whether they're metalloids, metals, or nonmetals fairly regularly over the course of like a decade. And so what ends up happening is really just if you're two sides on this line, know that it's not a metal, it's not a non-metal, it's a little bit of each, okay? And it may be classified at that moment as a metalloid, it may not. But it's not really fully one or the other. Okay, it has a few properties that are low.
So for your test purposes.
Yeah. I give you real clear stuff, like silicon, germanium sort of thing.
Okay.
Yeah. I don't do these tail ends where the properties tend to diverge, and depending on when the book was published, you'll get a different answer. Okay? There actually is a better test that's currently being done that hopefully will sort of put that a little bit to bed so they're not popping off and on like every few years. But yeah. We are working from a slightly old book this time. And so you could find books that are different, though it depends on which one's older, which one's actually considered more correct.
Oh, no, you Google it, it says it's not.
Yeah.
It's not.
No, that's fair. Yeah, these tail ends vary very much. Okay? And honestly, does it really matter? Not really, to be honest. Yeah. Yeah. The metal versus non-metals is a more distinct difference. Anything in this pathway here, just know that it's not fully one or the other. That's really the important part of that. Okay? Okay. Now, metals. Does anybody know anything about metals? Shiny. Very good. Non-metals? Non-shiny. Yeah. Non-metals don't have super clear properties, right? Basically, they're not metals. Yeah. Yeah. They don't have the properties that metals have, and so we literally just say not metals. Yeah, that's why everything here says metals on them. Yeah. Now notice that if we go down a group, we can go from non-metal, metalloid, into metal, okay? And that's because the division is diagonal going this direction. So top right, nonmetals, bottom left, metals, okay? Okay, so again, metals, shiny, very good. Definitely is one of their properties for very good reasons. Copper, gold, silver, well known for being shiny, famous for that, right? Jewelry typically made out of them because they're shiny and they don't corrode easily, right? Okay. They're ductile, meaning they can be shaped into wires. They're malleable, meaning they can be hammered into flat sheets. And again, this doesn't mean that you can bend them back and forth a bunch of times. It just means you could do that to them. Okay? They're good conductors of electricity. They're melted at much higher temperatures typically than nonmetals. Typically, they're solid at room temperature, with the exception being mercury, which is not solid at room temperature, which is in fact liquid, right? Okay. Was everybody okay with those? Okay, fantastic. Now, nonmetals, these are going to be things like hydrogen, carbon, nitrogen, oxygen, chlorine, sulfur. All of those are nonmetals. They're not usually shiny, they're not usually ductile, they're not usually malleable. They're often poor conductors of both heat and electricity. Are there exceptions to all these things? Yes. Okay? But in general, just think of it like this. Metals are basically all of these, right? If you get a pure sample of the metal. Okay? A nonmetal lacks most of these things. Okay? They're typically going to have low melting points and low densities. Can we find versions that we could argue this differently? Yeah, of course. But again, remember that nonmetals don't have the whole group. Okay? They have more exceptions. Okay. Except for aluminum, the elements along the zigzag line are usually considered metalloids. That's the normal definition given to you by the book. And again, just know that everything that touches that line has a bit of both properties, okay? It's on that cutoff point where you could argue, right? And so they oftentimes do get argued on and off of the metalloid series, okay? But they're going to include these according to your book here. They're going to exhibit some properties that are typical of metals and some typical of nonmetals. Again, our book is a little bit on the older side, so if you go on Google, there's going to be exceptions that they're no longer metalloids, okay? And apparently our book was published when most of these were metalloids, which is interesting because that's actually not been something widely true. So that's actually kind of interesting. I didn't realize it was published during that time. Exhibit some properties that are typical metals again, and some that are nonmetals. Typically are better conductors of heat and electricity than nonmetals, but not as good as metals. A lot of them are semiconductors actually, or can be made into semiconductors fairly easily. Okay? And this is because they can be modified to function as conductors or insulators, which is what semiconductor actually means. Okay? And so they're a bit of both. Notice that silicon and germanium being on that, right? Your computer chips are made out of silicon. Okay? Okay, and so these are some different characteristics of your metal and metalloid. There you go. It's just the same sort of thing we had talked about before. Can anybody give me arguments where they go, hey, this is an excellent conductor of electricity? How about diamonds? What are those made out of?
Carbon.
Carbon. And is it a good conductor of heat?
Yes.
Yeah. Is it shiny? Most people would consider it, yeah. And so, yeah, you can, that is carbon. That's an elemental form of carbon. And you can argue several points, but again, it's not a good conductor of electricity. You can argue other points against it, right? It's not malleable. If you try to hammer a diamond, you'll actually crack it and break it. And so all of the elements, about 20 are actually essential for the well-being and survival of human body. 4 of the elements make up 96% of our mass, and that is oxygen, carbon, hydrogen, and nitrogen. Okay. The macro minerals are these next ones, which is calcium, phosphorus, potassium, chlorine, sulfur, sodium, and magnesium. These are going to be involved in the formation of things like your bones, teeth, maintenance of heart and blood vessels, muscle contraction, nerve impulses, acid-base balance of your body fluids, regulation of cellular metabolism, etc. Okay? All right. Your other essential elements are actually called your microminerals or trace elements. That just means, it doesn't mean less important. It means you need less of them in your diet. Okay? So these things are mostly the transition metals. They're going to mostly be on period 4, silicon in period 3, and MO and I in period 5. These are going to be, again, present in the human body in very small amounts. Typically, if you were to take them and collect all of the ones from the human body, it would be like 100 milligrams, excuse me. Or water. Right. And so it's actually a very, very small amount if you look at the total mass of the human body, right? And you typically in your diet need these in microgram quantities, okay? But does anybody know what happens if you don't have things like iron in your diet?
You start getting lightheaded and stuff all the time?
Yeah, because you can't manufacture hemoglobin. It's also important for energy transfer. And so, like, you can't actually harvest energy. Yeah. So it becomes incredibly difficult to live. Yeah. So, remember, micro doesn't mean not important. Okay? Incredibly important, actually. By the way, you know that most food insecurity in the United States actually revolves around these, right? When you hear those numbers for there are so many people starving in the United States, it isn't this stuff that they're starving. They're getting plenty of carbs and stuff. It's that they're not getting this stuff right here, your microminerals. Okay, this right here is the table. It goes through these different quantities that you need and their functions. We'll start off here next time. You all have a good day. Have fun. Hopefully there's something interesting for the rest of the day.
Hey, Professor.
Hey, take care now. Wow, I'm tired.